We're the stronger than we look type. The braver than you think type. The type that sees the odds and says they're meant to be overcome. We're the progress is inevitable type. The rise to every challenge type. The type that knows bit by bit the future is certain to get better. We're the plan for a cure type. The improve life along the way type. The type that will stop at nothing. Absolutely nothing. Until type 1 becomes type none.
Welcome, everyone. My name is Jackie Casey, and I'm the Executive Director of JDRF MinnDakotas. I'm so incredibly pleased with tonight's turnout, where we have over 700 people in 5 locations who will benefit from hearing about the exciting research progress you're about to hear about tonight. Tonight's message is one of hope. Because of your past support, JDRF is able to share exciting, some may say amazing, research progress. When discoveries go into human clinical trials, it represents a catapult forward. You've helped make this possible, each and every one of you. And with your continued support, there will be more to come. I'm quickly approaching my 12 years here at JDRF, and what I'm amazed at each and every day is the profound passion and commitment embodied in our volunteers, people like you. Volunteers and philanthropy fuel JDRF's success nationally, at our chapter level, and in research progress. Many people would describe what we have as unbridled optimism, but I like to think of it as meliorism. Meliorism is the belief that the world can be made better by human effort. Meliorism is often described as the intermediary between optimism and pessimism, where good and bad outcomes are more passively expected. Meliorism, on the other hand, requires effort, hard work, passion, and commitment. It abounds at JDRF. We have absolutely no shortage of it. It's been perhaps expressed most famously by anthropologist Margaret Mead, who wrote that we should never doubt that a small group of thoughtful, committed citizens can change the world. Indeed, it's the only thing that ever has. And the only thing that she got wrong is that she never envisioned a group the size of JDRF and the impact that we can have collectively. In marketing lingo, meliorism is really a call to action. The vision video talks about the type we are at JDRF. We're the type that sees the odds and overcomes them. We rise to every challenge. With our action, progress is inevitable. Tonight, we hope to call you to action. We are asking each of you to be the engaged in a cure type. Oh, sorry, I must keep, there we go. Engaged looks like this. First, it's important to learn about the progress that JDRF is making because of your past and future support. You're doing that tonight. We offer opportunities like this throughout the year, including a newly launched Type 1 Nation event that will occur this coming November. Second, make JDRF a part of your personal philanthropy. Each year, thousands of people give and raise money through JDRF events, such as the Walk to Cure Diabetes, the Gala, and the Ride to Cure Diabetes. Our chapter has 4 walks in the Twin Cities, Rochester, Sioux Falls, and for the first time this fall, in Fargo-Moorhead. We host a gala, and we have a growing and robust Ride to Cure Diabetes team and JDRF Run Club. JDRF's spirit of engagement is no more evident than at these events. But events might not be for you. Thousands make gifts to JDRF each year. JDRF staff is available to talk to you about your giving. And if you're so inspired tonight, there's a giving envelope in your packet. And you can always give online. Many of you are at a place in life where you're thinking about your philanthropic legacy. Putting JDRF in your will or leaving us as a beneficiary in your life insurance policy are some easy ways for you to plan for a gift tomorrow for JDRF. We invite you to consider joining the Beta Society, JDRF's planned giving program. There's information in your packet, and again, staff is absolutely willing to discuss this with you. Your gift, at every level, at all levels, when combined with the gifts of the thousands of others, allows JDRF to put over $100 million every year to work on diabetes research around the world. Third, your gift is amplified when you go that next step and ask others to consider JDRF in their philanthropic priorities. Your confidence in our organization, your organization, will inspire others to give. It's important to remember that your gifts and the fundraising that you do is what fuels the important research progress that you're about to hear about tonight. Fourth, share your time and talent. JDRF could not accomplish all that it does without the generous support of volunteers. Volunteers at events, on committees, on the board drive our chapter success and JDRF's overall success. Their efforts, supported by the staff, help us host first-class engaging events, provide support services to newly diagnosed families and adults, and engage more people in our cause. Because of the time and talent shared by volunteers throughout JDRF, we are able to run effectively and efficiently, thus spending more donor dollars on research. Your packet contains an interest form that you can complete to tell us what kind of volunteering you might like to do with our organization, or to tell us what kind of information you would like to receive. Lastly, becoming an advocate is an important way to engage with JDRF. Our fundraising programs are the foundation for the diabetes research progress. However, alone, JDRF cannot fund all of the important research needed to achieve our mission. We must partner with others. Perhaps our most important partner is the United States government. Through our advocacy work, led largely by volunteers like you, we can influence our elected officials to vote on 3 types of critical issues. One is increased spending on diabetes research through such initiatives as the Special Diabetes Program, improved policies that support research, encouraging the FDA to approve technology and treatments in a timely manner, and health insurance coverage of those technologies and treatments. And lastly, removing barriers to research progress. Becoming an advocate is incredibly easy. Many of you may have met some of our advocacy team that were signing up advocates out in the hallway. It's very easy to become an advocate. If you didn't meet one of them and you aren't already an advocate, there again is a form in your packet. And you can get signed up that way. We make it fast and easy for your voice to be heard. And your voice is incredibly powerful. What we want, it's incredibly powerful, and it was demonstrated most recently by our efforts to remove barriers to the artificial pancreas with the FDA. What we want is for the products that will dramatically improve lives to have a reasonable pathway and to get quickly into the hands of physicians and patients. Many of you are already advocates. When you respond to advocacy alerts that you receive by email, it makes a huge difference. Thanks for lending your voice to these important efforts. One recent accomplishment, because of your efforts, was the recent passage of the Special Diabetes Program, one of the final acts of the 112th Congress. This was by far our most challenging year, with Congress grappling with many spending decisions and an extraordinarily difficult budget environment. Even with an extremely solid base of support and the many other campaign tactics that we used, we stood a chance of not passing this legislation. Failure to do so and to expand and extend this important program would have meant a significant cut in diabetes spending, which would have halted incredibly important research and wasted results thus far. Your voice made the difference, and we can't thank you enough for your efforts. JDRF MinnDakotas is made up of 3 states' efforts: Minnesota, North Dakota, and South Dakota. Tonight, 5 sites across our geography are all linked hearing this program. People here, Rochester, Duluth, Fargo-Moorhead, and Sioux Falls are all able to hear this hopeful message. We know that your engagement hinges on our ability to share the hope of research progress with you. This event allows us to do just that. Please join me in thanking Sanford Health, the Mayo Clinic, and Essentia Health for providing the sites where we were able to host these meetings. I'd also like to take a moment to thank our corporate and foundation partners whose support makes this event possible. Our premier partner for this event, Novo Nordisk, has demonstrated remarkable commitment to our constituent education about research progress. We also received a grant from the Richard M. Schultz Family Foundation to support the cost of this event and to support our greater outreach and education program. And our diabetes vendor partners join us at several times throughout the year to share the latest and greatest in diabetes technology and care with our constituents. And lastly, we couldn't have done any of this without the efforts of our extraordinary leadership volunteers at each of the sites. So please join me in thanking all of them for their support. Fueled by the generosity of our donors and partners, JDRF strives for a world without type 1 diabetes. Along the way, we promise to progressively remove the impact of this disease from people's lives so that they remain healthy and productive and free from complications. Diabetes isn't a simple disease. The plan for eliminating it is multifaceted. The video we are about to watch explains the elements of the plan for a world without type 1.
Type 1 diabetes, or T1D, is an autoimmune disease unrelated to diet or lifestyle that creates a lifelong dependence on injected insulin. It's a complex world filled with intensive daily physical and emotional struggles, ranging from carb counting, blood testing, and insulin dosing to the constant worry of life-threatening complications. With type 1 diabetes, there are no days off and there is no cure. But JDRF is working to change all this with a plan to turn type 1 into type none. In fact, we are the only global organization pursuing a strategic path of less until none, ensuring an ongoing stream of life-changing therapies that will lessen the impact of T1D until we can end it entirely. And we are working to bring real-world solutions to people as quickly as possible. Currently, JDRF's ongoing research programs total over $500 million around the world, and we're conducting 52 human clinical trials. And we've already made great progress on therapies that hold very real potential, such as artificial pancreas systems. They're revolutionary devices already in clinical trials that will automatically maintain blood glucose in a healthy range, allowing those with T1D to be able to tightly manage their dangerous highs and lows. Smart insulin, a once-daily treatment that senses glucose levels in the blood, turning on when it's needed and off when it's not, giving people perfect control without infusion sets and external devices. Encapsulation, a small packet implanted in the body that holds insulin-producing beta cells. A semi-permeable barrier protects the beta cells from the autoimmune attack while allowing the cells to detect glucose in the blood and release insulin, eliminating daily management for up to 2 years. Restoration, a true biologic cure. Restoration will return the beta cell mass to normal levels, all while fighting off the autoimmune attack, completely freeing people from T1D. And finally, prevention, halting T1D in its tracks and ultimately stopping it before it even starts. Creating a world where people no longer worry about the possibility that they or their children will develop the disease. We're the only T1D organization working at every stage of the drug discovery and delivery pipeline to ensure that these life-changing therapies get into the hands of those that need them as fast as possible, impacting people of all ages and at every stage of T1D. And while we've made significant progress to date, there's still a lot of work to be done, and we need your help. Support our efforts to create a world without T1D, and together we can turn Type 1 into Type None.
So you're getting the theme a little bit, Type 1 to Type None. It's something you're going to start hearing repeatedly from JDRF. It's our commitment to you, and we hope your commitment to progress forward. Tonight you're going to hear more specifically about encapsulation, but before you do, let's look at some of the elements of the JDRF plan. As noted in the video, JDRF is the only global organization with a strategy to move scientific advances from the laboratory into clinical trials and then into the hands of patients. Research can get stuck anywhere along this pipeline. Early in discovery research without a partner that's willing to make the investment to take it into clinical development, many therapies and treatments could die in that phase. Without partners like JDRF who have the expertise and the credibility and the relationships to work with entities like the FDA, many treatments and cures can get stuck in the regulatory phase. Ultimately, all of our goal is to deliver life-saving treatments and therapies into the hands of patients. And JDRF is working across that pipeline. Working across the pipeline is how we make the most out of our early investments in discovery science. By further investing in clinical development, regulatory intervention, and clinical trials, JDRF will ensure that treatments and therapies are delivered to patients. And that's how we create a world without Type 1 diabetes, from Type 1 to Type None. I think I'm going to skip because we may need to move ahead. It's only because of your generous support that JDRF is able to achieve these impressive research results. Your engagement in all of these ways will continue to fuel our progress. Tonight, we are thrilled to share with you progress being made in the area of encapsulation. Here, to share more comprehensive overview of encapsulation and the recent exciting progress is Dr. Albert Hua. Dr. Hua joined the JDRF staff in January of 2007 and is currently serving as a senior scientific program manager in the Beta Cell Therapies program, for which he develops and manages research initiatives related to islet cell transplantation, bioengineering, stem cell research, and encapsulation. Dr. Hua has extensive experience in program planning and implementation and has been involved in managing large research consortia, including the European Consortium for Islet Transplantation and the Islet Transplantation Program in Australia. He has recently established the JDRF Encapsulation Consortium in 2013. Prior to joining JDRF, he worked as a consultant and a research associate at the International Biometric Group, where he managed and executed research grants awarded by the United States government. Dr. Hua received his undergraduate degree in chemical engineering from Cornell University and his doctorate in bioengineering from the Massachusetts Institute of Technology. His dissertation focused on liver tissue engineering devices and physiological organ cultures. Please join me in welcoming Dr. Hua to JDRF MinnDakotas.
So this just goes on, just directly goes on. Okay.
Yep.
All right. Thanks, everybody, and thanks for coming. From what I heard, this was the first truly spring weekend, and you guys gave up, the time to hang out outside and wanted to be inside to hear me talk, so I appreciate that. So I hope I'll be able to give you a flavor of the several programs that JDRF is focusing on and how we are targeting these programs. And then after that, I will dig a little deeper into the encapsulation program. But first, just a little bit of facts about JDRF. We are the largest charitable funder of type 1 research worldwide, and we are a volunteer-driven organization. We have a volunteer-based board, so we're very patient-oriented. The goal, like Jackie said, we're trying to remove the burden of type 1 slowly but steadily from this world. And there are a lot of people like me. There are more than 20 people with either MDs or PhDs at the national office in the research department. Our job is mainly to use the funds that you guys help raise to spend it most wisely and most strategically so we can fund the best research to the best investigators. And you can see here on the graph here, in 2013, we were able to spend more than $100 million in research, and out of that, a significant portion is in encapsulation. So I will throw some charts out here tonight, so I hope you'll bear with me with some of these numbers and charts. So JDRF programs are sort of designed to target all different stages, and the way that we look at type 1 diabetes is across this spectrum depicted here. What you see on the left-hand side on the vertical bar is what we call beta cell mass. So we now know that type 1 diabetes is caused by the slowly decline of the mass of beta cells in the body. Beta cells are this type of cell in the body that secretes insulin. So once an autoimmune process starts, it starts to destroy these cells. And once you lose a significant portion of these cells, you start to have clinical symptoms of diabetes. And it's actually indicated here in a red line. So with an individual who may be still looks like he was healthy, but maybe at risk, he would have a very high or healthy level of beta cell mass. But as the type 1 diabetes disease starts to progress, the beta cell mass starts to decline. And once you reach this critical mass, below that, the amount of beta cells left in the body is no longer able to cope with the glucose fluctuations, then you actually would have the clinical symptoms. But along this pathway, the spectrum, we can divide the type 1 diabetes into these stages. So at the first stage, will be at risk. So these individuals will be probably genetically predispositioned to more likely to develop type 1 diabetes. And you can't really tell anything wrong with their beta cell mass, but then given the right environmental triggers, for example, diet or viral infection or lifestyle or stress, some kind of triggering event would happen. And then this individual would then enter what's called a pre-diabetes stage. And starting here, the mass of beta cells starts to decline. And that's because the autoimmune process has already started. The immune system starts to recognize these beta cells and starts to destroy them. And over time, so few cells left that they develop type 1 diabetes. And these people we call recent onset or new onset patients. And then, of course, the longer time, we call these patients established diabetes. So we look at this spectrum and determine the type of programs that would target these different stages. So the first stage, at the at-risk stage, we want to look at prevention to prevent the autoimmune process to ever start happening. And this is what we would call primary prevention. This is actually a very long-term goal because right now there's still not a very good way to identify truly those who are at risk and what would be the very targeted approach to prevent these people from developing type 1 diabetes. We're still learning a lot about the disease in order to determine that kind of treatment. So a secondary prevention is what we think is more achievable in the short term, where in the pre-diabetes stage, you can already detect signs of autoimmunity. You can detect these proteins in the blood called autoantibodies, which will be the markers that tells you that there is an autoimmune process ongoing that's targeting the beta cells specifically. If we can then determine those individuals that are already in this stage, maybe we can target immune-based therapies and also beta cell therapies to promote the health and survival of the beta cells. So then they can remain before this red line, and then they will not have the clinical symptoms of diabetes. But once diabetes is already determined and diagnosed, we are also looking at different ways to help individuals to manage their diabetes better. So Jackie mentioned smart insulin and artificial pancreas, and these are either mechanical means or chemical means to really help manage this daily burden. But we also have more biological means of restoring the beta cell mass. So one will be called restoration, which is trying to grow back the beta cells in the patient's own body and at the same time deal with the immune system so we will not have this ongoing attack on the beta cells. And encapsulation is really a different type of transplantation approach where you grow up the beta cells outside the body and then you transplant these beta cells into the patients with encapsulation technologies to really protect the cells for a very long time. So going a little deeper into the encapsulation program, what we really started with, and JDRF actually has been funding this area of research for a very long time, is pancreas and islet transplantation. And these are being practiced right now in the clinic. And the concept is really simple. Since these patients have lost a significant amount of their beta cells, let's put more cells back in these people's body and to boost up that beta cell mass. So I'm sure you're familiar with pancreas transplantation, which is like other organ transplantations. I'll explain a little bit about islet transplantation. So islets are clusters of cells in pancreas, and beta cells reside in these clusters. So what islet transplantation is to take a pancreas that's donated by a deceased donor, and then you can break up this organ and then isolate out these islet clusters. And then you infuse these clusters into the liver of a type 1 patient. And once these cells reside in the liver, they can start to sense the glucose level and start to secrete insulin. And there are already thousands of patients who have been treated with pancreas or islet transplants. And so we know it works. We know that by boosting the beta cell mass this way, by transplanting these cells, these patients can reestablish their insulin independence. They do not need to check their blood sugars as frequently, and then they don't need to inject themselves with insulin. So what does that really look like? So this is a visual representation of a patient's continuous glucose monitor for 3 days. And so the x-axis is time of the day, and then the y-axis is the glucose level. And then you can see the level is quite dramatic everywhere. There's a lot of high sugar, and there's a lot of low blood sugar. And then the hemoglobin A1C was very high at 8.9%. And this was before this patient received an islet transplant at the University of Pennsylvania. 1 year after the transplantation, you can see just visually the line is so much better, the glucose is so much better controlled, and the A1C is now at 5.5. And 4 years out, this patient is still very well controlled without any need to inject any insulin. So this is from an islet transplant, and we know that this works really well. And actually, islet transplant at some excellent centers, including the University of Minnesota, we now know that 5 years out from transplantation, more than 50% of the patients can still maintain their insulin independence. So this procedure works very well. So this may be considered as a cure by a lot of patients because you don't need to check your blood sugars or inject yourself with insulin anymore. But there are some limitations to this procedure. So number one, we're limited by the supply of healthy cells, healthy islets, or healthy pancreases. At any given year, I think there are only about 8,000 to 9,000 organ donors in the United States. And out of those people, maybe only about 1,000 of those pancreases will become available for whole pancreas transplant. And in terms of islet transplant, it's no more than 100 that are being done per year in the US. So this is never going to be able to satisfy the millions of type 1 patients out there. And the second limitation is that these cells are from another human being. So once they're transplanted into a person, just like any other organ transplant, like liver or kidney transplant, you have to take immune suppression in order to dampen the immune system so they don't reject the cells as foreign. So these drugs have a lot of side effects. They could affect your kidney function. They could affect your cardiovascular disease, and then they could enhance your cancer risk. So because of these significant risks, you cannot really justify the use of these drugs in relatively healthy type 1 patients. So the people who can really receive these procedures right now are those really sick type 1 patients who have life-threatening hypoglycemia unawareness. So there are only a very small population of people who can receive this. So these procedures provide the clinical proof of principle that by boosting the beta cell mass, by transplanting these cells, you can cure type 1 diabetes. But we would like to remove these limitations so then we can provide this treatment to a larger type 1 population. So which brings us to encapsulation. What are we talking about? What type of product or treatment are we really talking about? So this is a more complicated product than a pill that you may just take, in the morning. This would involve a cell source, which you can see here. There are some potential cell sources listed here. I'll go into more details in a later slide. We need to make sure these cells are unlimited so we can make a lot of them to treat patients. And then we need to make them at a level with consistent quality so the FDA would allow the approval of these cells to be transplanted. And once we have these cells, we want to be able to put them with some kind of encapsulation technology that will eliminate the use of immune suppression. So then you will have encapsulated cells transplanted into the body, but then you don't need to take these risky drugs that would give you those terrible side effects. So a lot of people ask me, what does the encapsulation look like? So a lot of people use this analogy here. So the sharks will be, in this case, will be like the surveilling immune cells that try to look for things that shouldn't be in your body. And then the diver, in this case, will be like an islet that you're trying to transplant into the patient. And we're trying to build a cage where the cage would protect the cell from the immune cell attack. But then the insulin and glucose and nutrients and oxygen should be able to move freely in and out of this cage so then you wouldn't have any impediment to the insulin delivery. So there's also biocompatibility issues that we must think about. The material has to be biocompatible. We don't want the body to have a foreign body response against the material and wall off the cage. the cells have to remain very viable and alive in this device. And then finally, we feel like the retrievability of such a device will be very desirable. Number one, if the cells have some kind of unforeseen event that you want to remove the cells, you want to be able to retrieve the entire device so then you don't leave any cells in the body. And number two, if the cells don't last forever and you may need to have a replacement device, you can take out this device and put in a new one. In terms of the requirements of the cells, we want to make sure we can make a lot of them, and then they need to be safe to be placed in human beings, and then we need to make sure that every batch that you make will be consistent. And they need to make insulin appropriately. We don't want them to make too much insulin. We want them to make insulin at the right time, deliver them at the right time, and fast enough to really counterbalance the glucose at the right time point. Otherwise, you may run into hypo or hyperglycemia. And then obviously, you need to be alive in the cage. And we think there are two cell sources right now that have the most potential for in the near future to go to the clinic. So one you may have heard a lot about is stem cells. So stem cells is a really broad term for a type of cell that have unlimited potential of growth. So you can grow buckets and buckets of these cells. So that's the number one criteria for being called a stem cell. And the number two is that stem cells have the capacity to become many different types of cells. So what most researchers are working on are either human embryonic stem cells or what's recently been made is human-induced pluripotent stem cells. And these two types of stem cells have the greatest capacity to turn into any type of cells in your body. They can become liver cells, skin cells, or in our case, we want to turn them into pancreatic beta cells. So a lot of advance has already been made with this type of cells. And another type of cell is already available now. We know how to raise millions of pigs, and then we can use the pancreas in these pigs to isolate these islet cells. So these are already available, and they're immediately functional. So I want to tell you a little bit of the significant progress to date in this area before I go into what's about to come, I think. So number one, like I said, multiple sources of cells have already been identified. There are companies and academic researchers that are working on pig cells as well as making beta cells or cells that are almost like beta cells from stem cells. There are multiple device types that are being developed right now. And there actually have been, and some clinical trials are ongoing right now to test encapsulated cell products. So a long time ago, I would say about 10 years ago, there are a few trials of using micro capsules, and these are really, really small little round capsules that would contain human islets, and these capsules were made out of alginate. Alginate is a very biocompatible material that's extracted out of algae, and they transplanted these microcapsules containing human islets into what's called a peritoneum, which is sort of like the abdominal cavity. So they saw no adverse effects, and they saw some inkling of functional response. For example, the C-peptide, which will be a marker for beta cell function, and they also saw some degree of reduction of insulin usage. But it didn't seem like the effect was very long-lasting. But again, this technology was very old. So that's the first one that I listed here by Calafiore and Tuck. And JDRF has supported this Australian company called Living Cell Technology to transplant porcine islets contained in alginate microcapsules as well, and transplant it also into the same site. I will go into a little bit more detail about this in a later slide. An investigator in Belgium called Denis Dufresne is currently testing human islets in an alginate sheet. So using the same type of material extracted from algae, instead of making them into capsules, he made them into a large sheet and a really flat structure, and then transplanted it into the under the skin. And he has done one patient in Belgium, and in a public meeting, he has presented data showing that significant reduction of insulin dosage was achieved. and it lasted for at least 10 months. Another investigator, also in Belgium, called Danny Pepeliers, he is also testing human islets in alginate made with alginate, and these are microcapsules, so again, the round little capsules, and he's transplanting them into this area called the omentum, also sort of in the stomach area, but then it's this fatty tissue that protects the organ. So the trial is ongoing. There's not as much data on that trial. There's a company called Beta O2 in Israel. They have a macro encapsulation device, which means a device that can contain thousands of cells. And their device is unique that it provides oxygen to the cells. So that you don't need to worry about getting oxygen through immediately through the human body. And they're testing this device with also human islets. And they did one patient in Germany, and this report was just published about half a year ago. And they showed that the cells remained viable for a very long time, I think also around 10 months. And at that time, they voluntarily removed the device in order to assess what's going on in the device. And there was function of the cells, but I think a larger trial will need to be done in order to really determine the efficacy of this approach. And finally, a biotech company called ViaCyte in San Diego in California is using human embryonic stem cells, and they make what's called beta cell progenitors. Progenitors are basically these cells that still have some growth potential, but they eventually should become pancreatic beta cells. So they made these progenitors and then put them in another kind of macroencapsulation device and transplanted them into various animal models. And then they showed that over time, these cells do become fully functional beta cells. And then I will also go into a little bit more detail in a later slide. So these are things that are either ongoing or happened before. And I'll go into what we're doing right now in the clinic and then what's about to come. So what JDRF thinks in this area is that I think there are a lot of different combination of product designs out there. So based on the level of immune suppression drugs that may be required and then the level of protection that can be offered by the encapsulation technology, this is how we sort of categorize the different product designs. So all the way on the left, you will still require full level of immunosuppression. So again, very high risk use of these drugs. And cells are already available today. Whole pancreas transplant, islet transplant, I already mentioned. So lies all the way on the left. This is already available in the clinic. As you move more to the right, we think the encapsulation technology will start to provide some of the protection and then would allow you to lower the use of immune suppression. So you would have either 3A or 3B kind of products where you use either porcine islets or cells derived from stem cells with some level of protection from encapsulation, but you may still need to use a low level of immune suppression. But of course, our ultimate goal and the ideal products would be all the way on the right, where you do not require any use of immune suppression. And then the encapsulation technology would allow the pig cells or stem cells to stay alive and functional for a very long time. And I will give you the two examples for product 4A and 4B. So 4A is using pig cells with encapsulation with no immunosuppression, and that's what I mentioned that we supported the company Living Cell Technology to do. And then product 4B would be encapsulation with cells derived from human embryonic stem cells, also without any use of immune suppression. And that's the company ViaCyte. So I'll start with ViaCyte. So this is a biotech company that we supported in partnership with the California Institute of Regenerative Medicine. So their product concept is they start with human embryonic stem cells, and this is just a microscope picture of these cells. They grow in clusters. And given the right recipe, which means giving these cells the right kind of drug agents and with the right timing at the right dosage and the right growth conditions, over 20, 30 days, you would then get to a stage that you obtain what they call these beta cell progenitors, which have the potential to expand and also differentiate and mature into fully functional beta cells. Once they obtain these progenitors, they put them in this macroencapsulation device, which they have designed so that nutrients and oxygen and all those important molecules can go in and out pretty freely. And they transplant this product into different animal models to test whether they can really correct diabetes. And what they found is that over a period of 1 to 3 months, so given enough time once they're transplanted, these progenitor cells, they do transform and then become these fully functional, what we call endocrine cells. So not just beta cells, but also alpha cells and all these other type of cells that are contained in an islet. And here is a picture of a cross-section of such a device. After the cell maturation, the insulin-producing beta cells are marked in blue. The alpha cells producing glucagon marked in red, and then another type of cell producing somatostatin in green. So this provides a proof of principle that this product, once you give it enough time after transplantation, they should be able to become functional, and they should be able to correct the diabetes. And it took me maybe only 30 seconds to go through this slide, but I want to emphasize that this work really took many, many years and many years of research investment. And I think JDRF should be credited for seizing an opportunity at the right time to really seed these research early on. So I'll tell you that, number one, these cells that ViaCyte is using, they're using a very specific embryonic stem cell line, which you have to use a line that's clinically applicable. Otherwise, the FDA will not allow you to test them in the clinic. And this line that they're using is called Cythera 49. And Cythera was actually a company that partnered with JDRF in 2004. If you remember, back in the late 90s, that was when human embryonic stem cells was first discovered and produced. There was a lot of interest in this research area, but then in the early 2000s, there was a federal mandate against the use of federal money to do research on human embryonic stem cells. But JDRF thought that this research is really important and it shouldn't be stopped. So then we stepped in, and then we funded many investigators in this area, and Cythera was one of these investigators. And with, at least partially with our money, they derived a number of human embryonic stem cell lines that are clinically applicable, and Cythera 49 was one of the lines. Cythera later merged and become part of the ViaCyte company, and then this is the line that ViaCyte is using to go toward the clinic. So remember that JDRF actually started this back in the early 2000s. And number two, even though I spent only 5 seconds on this chart here, which is what I call the recipe of producing these progenitor cells from these embryonic stem cells, this is a very complicated process, and then it took hundreds of researchers and many, many years to really come upon what is this recipe that's required to get the right cells. Because at any stage that if you use the wrong signal, you could get liver cells instead of pancreas cells. And one of the things that I think earlier was already shown on the slide is that JDRF not only just funds research, we also do a lot of advocacy work. In this case, since the year 1998, we were able to convince the United States government to appropriate the special diabetes program money toward the type 1 diabetes research. And here you can see in blue bars, these are individual years, the amount of the SDP money that was allocated. And starting from early on was $30 million per year to the last 10 years at $150 million per year, totaling to date more than $2 billion. And this was all directed, majority of it, toward type 1 diabetes research. And I would argue that a lot of that money was devoted into studying the developmental biology of beta cells without knowing how beta cells really develop from the embryo stage toward a fully mature cell. We can't really understand all the factors that would be necessary to create such a recipe to make these progenitor cells from these lines. So again, I just want to drive home the point that it's not, only several years of funding would help ViaCyte create this product. It's actually a lot of work behind these and over many, many years. So I mentioned that these cells mature after you transplant them into the mouse, and do they really correct diabetes? So this is an example, one of the example experiments that ViaCyte performed. So this is a chart that shows the glucose level of these mice that were transplanted with a device. But there were two groups of mice. The first group of mice is indicated in the green line. They received an empty device. Oops, sorry. They received an empty device without cells inside. And the second group of mice, they received the device containing the progenitor cells, and they call this product VC1. So you can see throughout most of the life of these mice, their blood glucose was relatively normal, below 200. And at week 33 after transplantation, they injected a chemical into these mice. And this chemical is very specific at killing the mouse beta cells. So normally, once you kill off the mouse beta cells, they would become diabetes. And this is a standard way of making a diabetic mouse model to study various therapies for diabetes. So in the case of the mice that received the empty device, once the mouse beta cells were destroyed, immediately they became hyperglycemic and diabetic because these devices contain no cells to control the glucose level of these mice. But in the case of those mice containing VC1, by week 33, all the cells in the device had already matured, and they can help control the glucose level in these mice. So even after destroying the beta cells in these mice, these mice still maintained their normal blood sugar. And what is really interesting is that mice actually have a different normal glucose level than human. So a normal mouse would have a glucose level roughly at here, around 150, while human actually is closer to 100. So when the mice were transplanted with the human cells, the mice, they had their glucose regulated at the human level. So this is an interesting side effect from this experiment. So the point of this experiment is just to show that by transplanting these cells, as long as you have, we think, enough cells, you should be able to control the diabetes. So no other intervention needed. So these mice did not require insulin injections, and we did not need to constantly check their blood sugar. And no immunosuppression was given to these mice. So what's next? So I think ViaCyte is at a stage where they have performed so much preclinical studies that it's really time to really look at how this will perform in a human being. And what they're doing right now is put together the necessary preclinical data to convince the FDA that this product is safe and it should have some efficacy for diabetes patients. And this package will convince the FDA that it is actually safe to test in a clinic. So they're currently putting this package together, and we're hoping that in this year they would send this to the FDA and they would get an approval hopefully soon. The first trial they will do is going to be a very small trial. And most importantly, we want to make sure that this product is safe. So the number one priority of this trial will be to find out whether it is safe. But I think this first trial will also tell us whether this is biocompatible in human, because there's not really any valid animal models to really tell us about the human immune responses against this type of products. So these early trial patients will really tell us whether the device will be compatible, whether the cells will actually function like we see them in mice, and then whether the device will actually be protective of the cells. So this is ongoing work with ViaCyte, and JDRF is in partner with ViaCyte in supporting this program. So remember the chart that I showed earlier. This will be product 4B, a product with encapsulation, cells from embryonic stem cells with no immunosuppression. Another product will be 4A, which will be using porcine cells instead of stem cell-derived cells. So this company, Living Cell Technologies, based in Australia, has been working on this problem for a while. And this picture shows these pig islets that have been stained in green, and then they are contained in these microcapsules made with alginate. And one of the unique aspects of their product is that they have this pig herd that's extremely healthy and contain very few viruses, and so we don't need to worry as much about transmission of these infectious agents from these pig cells to human. They transplanted these capsules containing pig cells into the peritoneum cavity, and JDRF supported in part of this trial in New Zealand, and the trial has already finished in New Zealand. And based on the public presentation by the company, they have found no significant safety issues, and then they were able to find some reduction of insulin dosage, and they were also finding that some of the patients, they had reduction of severe hypoglycemic events. So there's some benefit to this product, but then there was no true insulin independence from this. So I think there remains some optimization that can be had by improving the capsule design. And I think that there's a lot of opportunity here. So those are things, I think, that are sort of first generation. So these microcapsules have been around for a very long time. The device that ViaCyte has decided to go into the clinic with is based on a design that's really more than 10 or 20 years old. So there really haven't been a lot of new materials or new device designs. So what JDRF is doing right now is trying to support research that will give us that next generation encapsulation design. So we're focusing on novel materials, novel designs, and hybrid designs, and then funding research to help us understand what is the limitation of these current designs. And of course, if we find research progress that are really promising, we want to advance them through large animal studies and eventually in the clinic. And that is why we have started the JDRF Encapsulation Consortium starting last year. And as you can imagine, this field is, very complex. We require experts from all sorts of fields. We need people from the transplantation field, stem cell biology, immunology, engineers, and we need all of these people to work together. And one of the limitations that we feel in the past is that a lot of people work in isolation. They didn't really share information very freely. And this encapsulation consortium was established for us to really foster dialogue among all the researchers and then find complementary expertise so then we can put good teams together with complementary technologies. And so this was established in March 2013. And this is just a diagram of the different institutions that are involved in a consortium right now. And they're just categorized by the different focus areas that we're funding. And JDRF, in addition to providing research funds, we play a role in the middle to drive the sharing of data and protocols and hopefully reagents. And we want to drive some standardization in this field so that we can directly compare different technologies. And then at some point, we are thinking of providing a core facility in order to compare these technologies in a very independent fashion. So I want to give you a flavor of some of these next generation technologies that we're funding. So one of the things is these novel membranes with very defined pore sizes that you can use to create a macroencapsulation design. So here are some photographs under the microscope by Dr. Tejal Desai at UCSF. Excuse me. She was using either titania or silicon and alumina to create these nanoporous structures. And these pores are very defined, so then you can find the Goldilocks size where it's not too big where the immune cells may enter, or if it's too small that it may impede the insulin or glucose going in and out. So that's one project we're funding. Another project that we're funding is through Dr. Mark Poznansky at the Mass General Hospital. One of the ideas is to infuse these capsules with some type of drugs that would influence the immune system locally. So Dr. Poznansky, in this case, has infused these alginate capsules with CXCL12, and this is what we call the chemokine, which is a kind of molecule that would influence the activity of immune cells. So CXCL12 seems to do many, many things, and they all turn out to be quite beneficial for an islet transplant. So it seems to repel what we call T effector cells, which is the kind of immune cells that generally recognize a foreign cell and kill it. And it seems to drive that away. And it seems to attract T regulatory cells. And T regulatory cells are the type of immune cells that would protect an object or a cell in order for it not to be rejected. At the same time, CXCL12 seems to support the growth of blood vessels and also promote the survival of islets. And so here is a chart of one of the experiments that Dr. Poznansky has performed. So in this case, he's putting pig islets into these capsules, and he transplanted these capsules into diabetic mice. And the chart basically shows what's the percentage of the mice that remain diabetes-free. So this blue line here is basically just the capsules, but then without any of the CXCL12 added. So you can see within 50 days, all the mice became diabetic because 0% remain, healthy. And he tried different concentrations of CXCL12, and at a higher concentration of CXCL12, he was able to obtain more than 60% of long-term diabetes-free animals in this experiment. So in this case, he has obtained very, very interesting data, and through the consortium and a dialogue that JDRF has fostered, he actually has teamed up with Dr. Bernard Herring here at University of Minnesota to try to test this concept in a large non-human primate model to see if it also works in a large animal. So this is also very exciting. Another approach is being tested at the University of Miami. We're funding Dr. Camilo Ricordi to test this biohybrid device. This is basically a very multifunctional platform that would allow islet transplants and encapsulation. So in one case, you can modify this scaffold to release oxygen and to modify the surface, so then you can really protect the islets from immediate damage after transplantation. And the scaffold itself is very porous, so it acts as a mechanical support and distribution of the cells evenly, so they're not all clustered together. And finally, he's also working on nano thickness of encapsulation coating around the islets, so that will provide further immune protection. So this is happening at University of Miami. And finally, in terms of novel biomaterials, we're funding one of the key opinion leaders in the field of bioengineering, Dr. Bob Langer at MIT. And he has used this really sophisticated robot to perform thousands of different chemical reactions to generate novel biomaterials, and then using a very high throughput way to generate them and to screen through them to look for the most compatible ones that can be used for encapsulating islets. But in addition to providing research funding, JDRF also played a role to make sure that the project can actually be successful by providing the right expertise to this team. So Dr. Anderson and Dr. Langer at MIT, they are chemists and engineers, but they don't really know diabetes. They don't really know islet biology. So we teamed them up together with Dr. Gordon Weir at the Joslin Diabetes Center. So then they have input from him in terms of islet biology and transplantation. And we also put them together with Dr. Dale Greiner and David Harlan at the University of Massachusetts, so they can provide input on immunology and also the clinical management of diabetes. So that's another point I want to drive home, is that in addition to funding and advocacy, we also played a role in putting people together to make sure projects can succeed. So I think that's the last slide that I have, and I'll be happy to take questions.
Without your support, a world without type 1 diabetes is only a dream, and it's impossible to think that life will get better for generations to come. Because we know progress is uncertain. It's why we refuse to believe the struggle will eventually fade away. Relieving the constant counting, testing, and injecting is beyond our control, because life-changing discoveries are not our destiny. But your donation can change our destiny. Because life-changing discoveries are not beyond our control. We're leaving the constant counting, testing, and injecting. The struggle will eventually fade away. It's why we refuse to believe progress is uncertain, because we know, for generations to come, life will get better. And it's impossible to think that a world without type 1 diabetes is only a dream. Together, we can turn type 1 into type none. Join us now at jdrf.org.